Good morning, everyone. Today we're going to cover Chapter 6, so from 6.2 to 6.3. The whole purpose of this is to cover estimates where we have one sample and we're comparing it to our larger population. So sorry I can't be there today. I had to be away for a family thing. But you can always rewatch this and we'll cover the rest of this chapter on Thursday. So now we're moving into inferential statistics. And really what the whole purpose of this chapter and all later chapters is that we're using the sample data that we've collected to make inferences about our full population, right? So we've collected a sample, we have a statistic, and then what we're moving to is using that sample statistic to estimate the value of a population parameter, right? So we want to say, does our sample statistic really equal our true population parameter? And we're testing this hypothesis, right, about this population. So the first parts of Chapter 6 and 6.2 specifically is really covering population proportions, right? We're testing, does our sample proportion equal our population proportion? And then with 6.3 and on is, does this population mean that we've collected, does that equal our population mean? Okay. So given, for example, given our sample proportion, does it equal the estimate of the value of the population proportion? So we're going to start with Chapter 6.2. So like I mentioned, that this is about a population proportion. So our main objective of this section is, given a sample proportion, estimate the value of the population proportion, right? And that's given by the same notation that we say as P. And what really underlies these assumptions is that we assume that things are normally distributed, right? And because these are normally distributed, our sample distribution approximates the full population proportion. Okay, so that's what helps us in this chapter, is that because our sample proportion is equivalent, or it should estimate our population proportion because of that normal distribution. Okay, so let's move on to notation for proportions, right? So again, we're always using some sort of notation. Let me try to highlight. Before we've seen the P, right? And that gives us the proportion of successes in the entire population. Right? We've used P before to represent, how many times did you flip some heads over the times that you flipped the coin, right? Now we're saying that how many times does something is true within the full population, so all the possible parameters that could be true in this entire population. Okay, we use the p hat, and that's our notation for the sample, right? So our sample proportion of x successes in sample size n, right? So x over n, right? How many times did something come up true over the sample size that you have? Okay, q hat here is the sample proportion of failures in the sample size of n, right? So just 1 minus that p, or you can say, x minus the non-trials that didn't happen over the size of n. So specifically, let's give an example. If you're interested in red-green color blindness in terms of successes, right, we're saying how many of those are true, and we survey 80 of those men, and only 6 of them have red-green color blindness, right? Our sample proportion, the number of men in our sample, is 6 over 80, and that's 7.5%. Okay? Whereas Q, or the inverse of that happening, right, or the complement, is 1 minus 0.75, so 92.5% of men have red-green color blindness. Right. So like I mentioned, remember, is that the whole purpose of us doing this is that we're approximating to a larger population, right? But we do have to say that if this is truly normal, if we can use a proportion to estimate our full population, we have to make sure that it is normally distributed, right? And so these are 3 conditions that we have to fulfill. So first is that the sample is a simple random sample. 2, the conditions for the binomial distribution are satisfied. The same thing that we've done before, right? Is that there are a fixed number of trials that we have, right? A total of n. Each trial is independent from each other, right? There are only 2 categories of outcomes, which we would call a success or a failure, and those probabilities are constant across each trial. Thirdly, the normal distribution can be used to approximate the sample proportions because n times p is greater than 5 and n times q is greater than 5 are both satisfied. Right? We're just saying that do we have some sort of sample that's large enough that it could most likely be used to approximate the normal distribution? Okay, so remember these three assumptions. So let's be a little bit, let's clarify a couple more terms, right, that we've used before, right, where a proportion can be expressed as a probability and a percent, right? That just because they look different doesn't mean they're different concepts. P can represent that proportion, or it's a probability, right? So because things have occurred over some set of sample that you have, that's the likeliness of something happening. That's why we call it a probability, okay? And then we can call it a percent, where we just moved the points over to express it as a percentage of a value. Okay. So again, remember, our best estimate of the proportion is p hat, right? So we say that our sample of p hat represents our population, and we call this a point estimate. Okay, so this point estimate is the single value which is used to approximate a population parameter. So it tells us this is the closest value that we can use. So if we've sampled 40 people, this is what most likely represents the underlying population that we have. Okay. This is the same example as before, right? So now we can express it either as a proportion, a probability, or a percent, right? So regardless of what you're doing, if you say you have those 80 men and 6 have red-green color blindness, that sample proportion, even though it's 7.5% or 0.075, that should represent our population proportion of what's happening. Okay, so let's be a little bit more specific and use the notation that we're given. When we're given the sample proportion of p hat, we don't need to calculate the x over n. Same thing, right? So an example, we are told in this chapter problem, it's reported that 580 peas are obtained and 26.2% of them have yellow pods. So this is given to you as a percentage, which I'm asking you to convert to a proportion or probability, but that's already expressed for you in terms of the p hat, right? So it's 0.262, and the q is just 1 minus that value, right? So 73.8%. Again, we've seen this, right? That the population proportion is always best estimate is p hat, and we call that a point estimate. So a vocab term for you to remember. All right, so you can work through these. The same question, right? If I'm already giving it to you, you know what a p hat is in terms of what a population value is going to be. So let's move a little bit into what we call confidence intervals. So confidence intervals are related to how we sample from our full population and what we're doing in terms of collecting the true population parameter from our sample. So a confidence interval is important because it tells us how good or bad our point estimate is. So we call that precision. So are we measuring the true population parameter given our sample? Okay, so this gives us the range of possible values for the population parameter. So the true population parameter may fall within this given interval around the point estimate that we've collected. So remember, we said that that point estimate is just that one value that we've collected from our sample, and that should estimate the true population parameter. Our confidence interval is a range of values around that point estimate that tells us where that true population parameter may be. Okay, so just to define this in a term that you should remember, it's the range of values used to estimate the true value of the population parameter. Okay, and we'll get to that a little bit more specifically in a couple of slides. Okay, confidence intervals are associated with confidence levels, right? And so most commonly are used in most social sciences, health, behavior, health related studies are 95% and 99%. So our alpha level, or alpha given here in Greek notation, represents our confidence level. So our 95% confidence level corresponds to an alpha of 0.05, or a 5% alpha, and our 99% confidence level corresponds to an alpha of 0.01, or a 1% alpha. Okay. So what we're saying in terms of an alpha, that's our error where the confidence level corresponds to how confident we are, right? So they're just opposite terms of each other. If we're 95% confident, we have a 5% chance of error, right, with our alpha. If we have a 99% confidence level, we have an alpha of 0.1. This is our error of 0.1, or 1% amount of error. So remember the difference between the two. They're related, but slightly different concepts. Okay, I'll cover that more in just a couple of slides. Our confidence level, to be more specific, is the probability that the proportion of times that the confidence interval contains the population parameter. Okay, so what we're saying is that if we have a confidence level, if we were to do this study an infinite number of times, the confidence interval that we've calculated will contain the true population parameter. So this will make sense when we show some confidence intervals. So I'll get to those in just a couple of slides. Okay. So how we calculate confidence intervals and confidence levels depends on how we create and use our critical values, which we've already done in the past chapters. Okay. So we usually used a standard z-score, right? And that tells us whether sample statistics that are likely to occur and those that are unlikely to occur, right? So those that are unlikely to occur, we cut off at a point called our critical value. Okay, so critical values are based on the following observations. Sampling distribution of a sample proportions can be approximated by a normal distribution, right? We made that assumption in the past few slides. Okay, is that sample proportions have a relatively small chance of falling in one of the red tails. Okay, so you can see here, right, we said that things that are far out and far extreme on the tails are really unlikely to occur, right? These things are way out on the edges. They are less likely to be close to the mean, right? The probability of the mean happening is 50%, right? Because it's right in the middle. Things that are farther out are a lot less likely to occur. It's far away. So we use our critical value of alpha, but we do an alpha divided by 2 because we are dividing the amount of error that we have into both sides of the curve, right? There's error that's out here and then error out on the left side and the right side. Okay. So we denote that area of the shaded tail by alpha over 2, and we see that the total probability of alpha is that sample proportion will fall into either of those two red tails, right? So that those extreme values will fall way outside. Okay, so remember we said that 2 standard deviations away was pretty extreme in terms of being far away, right? So we could say that anything more extreme than a 2, right, could be our range for a critical value, either on the positive 2 or a negative 2, right? If it's far away, those are extreme critical values, so they are unlikely to occur in terms of being close to the mean. Okay. So we say that, let's continue our definition of what a critical value is. By the rule of complements, there's a probability of 1 minus alpha that a sample proportion will fall within the inner green shaded region. So remember, we set the alpha usually to be 5%, right? So that means the 1 minus alpha would be 95%, right? So 95% of the time, the probability will fall within the region that we've set, right, in that green area. Okay. So then that z-score that separates the right tail region is commonly called the z with alpha over 2, and that's our critical value because it's on the borderline separating the sample proportions that are likely to occur from those that are unlikely to occur. So right, our cutoff is going to be at the extreme tails, right? That if it's over that tail, we say that's beyond or at the critical value. Okay, so let's get to this a little bit more specifically. Boundaries that identify the point in a distribution are considered unusual, right? Where those extremes are unusual. And we just basically look up our z-score to determine which one is going to be a critical value. And this separates the regions in the distributions that are deemed low probability areas, right? So these values separate sample statistics that are likely to occur from those that are unlikely to occur by chance alone. So here's the notation where we use the z in the right tail as the positive side, and the z in the negative as the left tail. Okay, so our most commonly z-score critical values are, so if we use the 95%, right, we have 5% on each, 5% total in terms of our alpha. So that means we divided that by 2, right? So now what we're looking at is a 0.25% alpha on each side, right? So that would, if you look at your table, you could look for the 0.975, which separates the left side to the right side, right? If you're looking on the right tail. And then if you're looking at the left tail, you would just look for 0.025. And on either end, that would correspond to a z of 1.96, okay? Right, you could try the same for the 99% and see if that corresponds the same way, right? Where you would look for 1% as a cutoff, and that should give you a z-score of 2.58 on the right side. And then if you looked for it on the negative side, the 1%, that would give you a negative 2.58 right here. So do that as a test right now and see if you get the same z-scores that I'm getting here. So more specifically, you can see the answer from the example that I told you to do in the previous slide, where the 95% confidence level corresponds to an alpha of 0.05, right? But remember, we said we're dividing this by 2 because we are using both ends of the tail. So we're saying that each side of the tail has 2.5%, right? Each side of the tails have 2.5%. So again, go ahead and look up where 2.5% corresponds to in terms of a z-score, and you should get negative 1.96 on the left side of the table and 1.96 on the right side of the table. So a couple more concepts before we start calculating confidence intervals and testing what we've been doing is a margin of error, right? So this is the difference between the sample proportion and the population proportion, right? We've talked a little bit about this where we've called terms that are when we measure differences between our sample and our population, right? But here we're being more specific where there's the difference between the sample proportion and the population proportion is some sort of error, and we call that the margin of error. And that's just saying what's the difference between the observed sample population, right, our point estimate of p hat, and the true value of the population proportion of just p, right? And that's given by this formula here. So it's basically just saying, given the confidence interval that or the confidence level that we're going to select, what's the maximum difference between our population and our sample that we could observe. So remember this formula here. So let's construct a confidence interval for p. So given the critical value that we've set that corresponds to some sort of desired level, so for here we're saying 1.96 for 95%, let's calculate the margin of error, and then let's also calculate the upper and lower bounds of the confidence interval, right? So we are given for instance, if you have a sample of 580 and I told you that the point estimate of the proportion is 0.26, what's the confidence interval? So I've told you to use an alpha of 0.05, which tells you that the critical z-score is going to be 1.96. So here's the formula from before, where we just use the z alpha over 2 times the square root of the point estimate times the q of the point estimate over n. And that is given by here of 0.034. So then we just plus minus our confidence interval as shown here. That's the calculation or the formula. And that's saying it's 0.228 to 0.296. So you can see that our population proportion falls right within our confidence interval, right? So it's right in the middle of 0.228 to 0.296. Of that value of 0.26, okay? Or you can give that as 0.26 plus minus the margin of error that you're calculating. So what does this mean? When we interpret a confidence interval or the margin of error, we are saying that we are 95% confident that the interval from 0.228 to 0.296 actually contains the true value of p, which is the true population value. So if we took 100 samples, if we did 100 studies of this, in 95% of them, the true population proportion would fall between these values. The wider the confidence interval, the less precise our sample estimate is, right? So if you knew that it was, your point estimate was 0.26, and you got a confidence interval that was 0.25 to 0.27, you're pretty close at estimating the true population parameter, right? You're right within the range of 25% to 27% of some, condition or some outcome happening, right? If you measured your population, excuse me, sorry, if you measured your confidence interval to be, 0.1 to 0.9, you're just saying that all the possible values could exist between 0.1 and 0.9 in the true population. So remember, the smaller you are, the more precise you are in terms of confidence interval. Okay. So the best way to do this is just to think about the formula that you have. Just use this formula. We are blank confidence level, confident that the interval from blank to blank contains the true value of the population proportion of P. Okay. So if you're asked any question, you can just use this formula, just fill in the values of things that you've collected. All right. So why don't you all try this and do this example, and we'll go over this in class next time. But this is asking, in a clinical trial, there are 370 babies that were born and 296 of them were girls. Use the sample data to construct a 99% confidence interval based estimate of the percentage of girls born. Based on this result, does this method appear to be effective? Okay, and you would set when you think this is the confidence level and the critical values you would need, and whether this is a precise estimate or not. Another example that you can try here, and we'll go over, so in the week before and after a holiday, there were 11,000 deaths, and 5,000 of them occurred in the week before the holiday. So construct a 90% confidence interval estimate of the proportion of deaths in the week before the holiday to the total deaths in the week before and then the week after. Okay. So remember these formulas, right? Is if the confidence interval is already known, we can calculate the P, right, or our point estimate, which you would just take as the middle value, right? So you would just get the middle part, or doing the same thing as calculating the midpoint of the 2 points. So we would just do the upper confidence limit plus the lower confidence limit and divide that by 2. Okay. If we have the confidence limits, we can also find the margin of error, right? It's just telling us how large is the range of error values that we have, right? So you just kind of, again, try to find that midpoint, but it's the range of possible values. So you would take the upper confidence limit minus the lower confidence limit and divide that by 2. So what we're going to be doing in this section of 6.3 and basically moving forward is when we're estimating a population mean when the variance or the standard deviation is known. Sorry, that should be a lowercase sigma. So what are our requirements for estimating the mean when we know our sigma? Okay, so again, this is the same thing. Does our sample estimate our population parameter, right? But here we're moving towards a mean. Before we were taking differences in our proportions, and now we're saying, does our mean equal the population mean? Okay, so what we're saying is there are a couple requirements. Is that the sample is a simple random sample, which we should always hope it is. 2, the value of the population standard deviation is known, right? And that either of these conditions are satisfied, where the population is normally distributed or where n is greater than 30. And if you all remember, when n is greater than 30, we can invoke the central limit theorem that says that for the most part, if what the original sample that this comes from is truly normal, 30 should make it approximately normal. Okay. And like I said again, right, is that we assume that we have a normal distribution invoking the central limit theorem, or the CLT. Okay, so that the mean of our sample means, or M, or X bar, is the best estimate for the population mean. So you can see how all these concepts are getting pretty similar in terms of how they're related, right? That we're really saying, does our sample equal our population? And for the most part, it should. And we can see with some error that it does. So like we've seen before, in terms of calculating our confidence interval for a proportion, we're going to do the same thing but do it for a mean, right? So we're saying, what's the success rate of the procedures that we've used to construct the confidence interval? Or, given our sample values, how close is it in terms of measuring the true underlying population mean? Okay, so like a confidence interval that we've used before, it's just really what's the difference between our sample to our population, and that's just given by our margin of error / confidence interval. And that's given by the formula here, where we use E equals some sort of critical value in terms of how confident do we want to be times our standard deviation. So constructing our confidence interval for mu is pretty straightforward. We find the critical value, so whatever value we choose to use. We calculate the E, then we calculate the confidence interval, which is just the mean plus or minus that margin of error that we're given. So try this example out here. Given a sigma of 0.62 with 106 participants, given our mean of 9.8 in our sample, what's the confidence interval at the 99% level? So we know that a z of alpha over 2 with our 99% level is given at the critical value of 2.58. So make sure you can find this value in your book and know for what level you'd like to calculate this at. Okay, and use your formula that's given before to multiply that out, and that's our margin of error of 0.155. Okay, so our confidence interval is therefore just the mean, or our point estimate given here of 0.982 plus or minus our margin of error, which is 0.155. Okay, so then it's ranging from 98.04 to 98.36, or given by the value plus or minus the margin of error. So that's saying that we're 99% confident that the interval from 98.04 to 98.36 contains the true value of the population mean, right? So that the population mean is within this range of 0.9804 to 0.936. So you can tell that it's a pretty small range, and that the true population parameter might exist within that range. So try this example on your own, where people have died in a boat, and because of the obsolete estimate of the mean weight of men was used. So in recent decades, the mean weight of men has increased. The data obtained from a simple random sample is as follows, where x is 40, n is 40 with the mean of 72.55. Research suggests that the population of weights of men has a standard deviation of 26 pounds. So find the best point estimate first of the mean weight of all those men. Construct a 95% confidence interval estimate of the mean weight, and then interpret that value. All right, so the solutions are given on the next slide, but try this yourself first. Okay, so are our requirements satisfied? So remember, these are assumptions that we have to satisfy. Is it a simple random sample? Check. Is the value of the population standard deviation known of 26? Check. Right? Our sample size is 40, so it's greater than 30, so we can make the assumption that it's probably normally distributed. So you're already given a lot of these values, right? So we're saying that the sample mean is 172.55, which is the best point estimate for the mean weight of all men, right, in the population. Right? So from our sample, we're saying this sample that we've collected from 40 represents the true population value of 172.55. Okay. So now I asked you to calculate the confidence level. So make sure that you can find the alpha of 0.05, and can you get the correct z-score that corresponds to that alpha? right? So remember, we're dividing it by 2 because it's both sides of the curve. Okay, then you're just going to plug that straight into your margin of error formula, and you would get a value of 8.0574 dot dot dot. Okay, with our x bar of 172.55 and our margin of error as given, we can construct the confidence interval as follows, right? So it's x bar plus minus the margin of error. So when you solve that, our range goes from 164.49 and 180.61. Be sure to just use the same formula for filling out the answer as what I've given you before, but now we're using it in terms of the population mean. So we are blank confident that the interval from the lower confidence interval to the upper confidence interval contains the true value of the population mean, or mu. Right? So given our answers from before, we would say that we are 95% confident that the interval from 164.49 to 180.61 contains the true value of the population mean. Right? So remember, our sample mean or our point estimate falls right in the middle of those two values. One last example is finding the margins of errors and confidence intervals again. So again, try this. Ages of drivers occupying the passing lane while driving 25 miles an hour with the left signal flashing. Calculate the 99% confidence level of this with an n of 50, an x bar or mean of 80.5, and the sigma, right, the known population sigma is known to be 4.6 years. So do the same things before. And here's another example. Be sure to try this one as well with 99% confidence with an n of 28, an x bar of $45,000. The population is known to be normally distributed, and the sigma, or the population sigma, is known to be $9,900. Okay, so that's the end of sections 6.2 to 6.3. So you can see what we're doing in these chapters and on is, does our sample represent our population, right? And how close is it? So, you can see from our confidence intervals and our margins of errors is how good are we at measuring our population given a sample of some value. All right, so I hope you all enjoy your day of not coming to class tomorrow, but feel free to email me with questions and I will get back to you as soon as possible. Thank you.